What kind of planet rolls through space on its side, hides a crooked magnetic field deep inside, may turn methane into falling diamonds, and still remains one of the least understood worlds in the solar system tonight? We travel to Uranus, a pale blue ice giant so strange that it does not just look unusual, it challenges the rules planetary science once thought were simple. If quiet cosmic mysteries like this are your kind of journey, please take a moment to like the video, subscribe, and share it with someone who loves space as much as you do. And truly, thank you for spending your time here. Before we begin, it would be lovely to know what time is it where you are, and from what part of the world are you listening or watching tonight. Leave a comment below and say hello. Now, with the distant sun fading behind us, let us drift outward and step into the strange and tilted world of Uranus. At first glance, Uranus seems to offer very little. It appears as a smooth blue-green disk far beyond Jupiter and Saturn, dim in ordinary telescopes, quiet in comparison with the striped violence of the gas giants, and so distant from the sun that sunlight there has already thinned into something weak and pale. Yet this subdued appearance hides one of the strangest arrangements in the solar system. Uranus does not spin in the upright, almost disciplined way that planetary science first teaches as normal. It turns with its axis tipped by about 98 degrees, so far from the usual posture that the planet seems less like a world rotating beneath its sky, and more like a globe that has fallen over and continues its journey while lying nearly on its side. That single fact is unusual enough to define the planet, but it is only the beginning, because once a world is tilted that far, the consequences spread into everything around it. They spread into the shape of its seasons, the behavior of its atmosphere, the pattern of light across its cloud tops, the orientation of its moons, the architecture of its magnetic field, and perhaps even into the deeper question of how such a planet forms at all. Uranus is not merely an odd outer planet. It is a case that unsettles the tidy expectation that the major worlds of the solar system should all follow roughly the same physical rules in roughly the same way. Most planets preserve a recognizable relationship between their spin and their orbit. They circle the sun in one broad plane, and though each has its own axial tilt, the tilts are generally modest enough that the planets still look stable in the ordinary sense, like spinning bodies whose poles remain meaningfully above and below the plane of travel. Earth is tilted, Mars is tilted, Saturn is tilted, and those inclinations matter, but none of them overturn the basic picture. Uranus does. Its north and south poles do not sit like calm markers at the top and bottom of a familiar globe. For long portions of its 84-year journey around the sun, one pole is turned almost directly sunward, while the other faces into darkness, and the geometry becomes so unfamiliar that the usual language of sunrise and sunset begins to lose its easy meaning. At solstice, the poles can receive decades of continuous illumination or darkness, while regions nearer the equator pass through a far stranger routine, with the sun skimming low and behaving in ways that would feel almost impossible on the terrestrial planets. A Uranian year lasts longer than a human lifetime, and because the planet rotates once in roughly 17 hours, its daily motion is fast while its seasonal motion is almost geologically slow by human standards. These two clocks, one rapid and one immense, are forced to coexist on a world whose axis is nearly parallel to the plane of its orbit. The result is not just a more extreme version of earthly seasons, it is a different seasonal logic altogether. What makes Uranus especially important is that the tilt is not an isolated curiosity. It creates a chain of consequences that keeps pressing planetary scientists toward harder questions. On average, the poles receive more solar energy than the equator over the course of a Uranian year, a pattern that already sounds like a reversal of expectation. Yet the atmosphere does not always respond in the simple way that this geometry suggests. Temperature patterns, Cloud behavior, wind structure, and long-term circulation do not line up neatly with the incoming sunlight. And that mismatch matters because it hints that the visible oddity of Uranus may be connected to deeper oddities below the clouds. A world can look unusual from the outside and still be ordinary in its inner workings. Uranus has never been easy to dismiss that way, even before the details are fully understood. The tilt keeps implying that something fundamental in the planet's history was violent, exceptional, or both. The most widely discussed explanation is that Uranus did not begin this way. It may have been struck early in its history by a massive protoplanet, perhaps something around the size of Earth, in a collision powerful enough to shove the entire world into its sideways posture. That idea has a certain elegance because it links a visible modern fact to the chaotic youth of the solar system, when impacts were common and planetary bodies were still competing for stable form. But elegance is not proof. A single giant impact may not explain every detail. Some models favour multiple collisions rather than one. Others suggest more complicated interactions between formation, migration, and internal structure. The difficulty is not only finding a mechanism that can tip a planet. The difficulty is finding one that tips the planet without destroying the broader system that still surrounds it, including its moons, its interior layering, and the features that appear to have persisted for billions of years. That distinction matters because Uranus is not simply a damaged world. It is a functioning planet whose abnormal orientation has become the baseline condition for everything else that follows. Its moons orbit in the same tipped arrangement. Its ring system shares the skewed geometry. Its seasons have been unfolding under these conditions for vast stretches of time. Whatever happened to Uranus was not a brief accident with limited consequences. It became the organizing fact of the planet's existence. Seen from that perspective, the tilt is less like a dramatic event preserved in memory and more like a permanent rewrite of planetary identity. There is also something quietly destabilizing in the contrast between Uranus and Neptune. The two planets are often grouped together as ice giants because they are similar in size, mass range, and broad composition, and in many textbooks they appear almost as a pair. Two cold outer worlds beyond Saturn, similar enough to be treated as relatives. Yet Uranus refuses to behave like the simpler half of that pairing. Neptune radiates more internal heat, drives more obvious atmospheric activity, and presents a more conventional axial tilt. Uranus, by contrast, appears underluminous, less internally active than expected, and catastrophically off-axis. Two planets that seem comparable from a distance begin to diverge in ways that matter deeply to theory. If ice giants are meant to represent a coherent planetary class, Uranus complicates the category from within. It suggests that size and composition are not enough, that planetary history can alter the final outcome so completely that two neighbouring types may end up obeying different practical rules. This is one reason Uranus has become more important with time rather than less. In earlier centuries it expanded the known boundary of the solar system. Later it helped expose irregularities in orbital prediction and contributed indirectly to the discovery of Neptune. In modern planetary science, it has become something else again, a reminder that even a major planet can remain underexplored and conceptually unsettled. Only one spacecraft has ever visited it at close range. Most of what is known comes from telescopic observation, careful modelling, and the effort to infer structure from limited signals. That scarcity of direct data gives Uranus an unusual scientific presence. It is not mysterious because nothing is known. It is mysterious because enough is known to see the contradictions, but not enough is known to resolve them. A planet that appears visually bland becomes, under closer study, one of the least tidy objects in the solar system. Its rotation challenges common expectations. Its seasons stretch ordinary language beyond comfort. Its energy balance resists easy interpretation. Its very posture suggests an ancient disturbance whose exact nature remains unsettled. And because these features are not minor details but system-wide conditions, Uranus keeps forcing a broader reconsideration of what counts as normal in planetary evolution. The familiar model of planets as orderly spheres, each tilted a little, heated a little, and arranged according to broadly similar dynamics, begins to look more provisional when Uranus enters the frame. It is still a planet, still governed by gravity, momentum, radiation, chemistry, and time. Nothing about it breaks physics. What it breaks is expectation. It breaks the quiet assumption that the major world should differ only by degree rather than by kind of behaviour. On Uranus, the difference is structural. A planet can fall sideways and remain stable. A planet can endure an ancient upheaval and turn that upheaval into its long-term pattern. A planet can look calm while carrying the marks of a much stranger past. By the end of this first encounter, Uranus no longer feels like a remote blue afterthought at the edge of the Sun's domain. It feels like a challenge placed there in plain view. A world whose silence hides a deep rearrangement of the rules by which planetary order is usually imagined. In the spring of 1781, Uranus entered modern astronomy not as a triumph of certainty, but as an object that did not look quite right. When William Herschel observed it through his telescope, the new point of light did not behave like an ordinary star, it showed a small disk, and that subtle difference mattered. At first it was taken for a comet, because the catalogue of known planets seemed complete enough that another major world was not the obvious answer. Yet as more observations accumulated, the object refused the path of a comet as well. Its orbit was too regular, too broad, too planetary. What had seemed at first like a minor irregularity in the star field became something much larger, a new planet, the first to be discovered in modern times. That alone would have secured Uranus a permanent place in scientific history. Until then, the planets visible to the unaided eye had formed a closed classical set, known since antiquity and woven so deeply into human thought that they felt almost final. Uranus broke that inherited boundary. It expanded the solar system in a single step and revealed that the familiar arrangement of worlds was not complete after all. But even that was not the strangest part of its story. The deeper peculiarity came later, when Uranus began to misbehave in a more technical and much more consequential way. Once astronomers accepted Uranus as a planet, they tried to do what astronomy had learned to do very well by that period. They calculated its orbit. Newtonian gravity had transformed celestial motion into something that could be predicted with remarkable precision, and the planets were no longer only wandering lights against the sky. They were bodies whose future positions could be projected mathematically if enough information was gathered and the relevant gravitational influences were included. Uranus should have fit into that framework. It was distant, slow, and faint, but it was still a planet moving under the same laws as the others. For a while, it seemed to cooperate. Then the discrepancies began to matter. The observed position of Uranus did not remain perfectly aligned with the position predicted from existing calculations. At first, these mismatches could be treated cautiously. Astronomical observations are never free of error, and a newly recognized planet with a long orbit is difficult to constrain quickly. Uranus takes 84 Earth years to travel once around the Sun, which meant that even decades of careful watching only captured a fraction of its path. Older observations, once it was realized that Uranus had been recorded earlier and mistaken for a star, helped extend the record backward. But the longer the effort continued, the more stubborn the problem became. Uranus was not where it ought to have been, at least not with the consistency that the model demanded. The difference was small in absolute terms. But in planetary mechanics, small departures can become profound. They raise a difficult question. Is the theory wrong, or is the inventory incomplete by the early 19th century? Many astronomers favoured the second answer. The laws of gravitation had proved themselves too powerful across too many cases to abandon lightly. If Uranus wandered from its predicted path, perhaps it was not defying Newton after all. Perhaps something unseen, something farther out, was tugging on it. This was a daring idea, but also a disciplined one. It didn't appeal to mystery in the empty sense. It appealed to causation. A deviation in motion implied a force implied mass. If that mass belonged to an unknown planet, then the problem could in principle be run backward. Instead of beginning with a planet and calculating the orbit, astronomers could begin with the orbital disturbance and infer the planet. This was a remarkable inversion of the ordinary logic of discovery. Rather than seeing a world and then describing its motion, they would study motion and then predict the world. Among those who pursued this problem, two names became central: John Couch Adams in Britain and Urbain Le Verrier in France. Working independently, they used the irregularities in Uranus's orbit to estimate where a perturbing planet might lie. The task was not simple. The deviations were slight, the data were imperfect, and any inferred planet had to be assigned a plausible distance, mass, and orbital path before its gravitational effects could be tested against observation. This was celestial mechanics at its most ambitious, where mathematics reached outward beyond the edge of sight. When Johann Galle, working in Berlin, finally located Neptune in 1846 very near the position predicted from these calculations, the result became one of the great moments in the history of science. A planet had been discovered not because it first appeared in a telescope by chance, but because Uranus had betrayed its presence through a persistent failure to obey expectation. That distinction matters because it changed what a planet could be scientifically. A planet was no longer only a visible thing awaiting detection. It could be an inferred cause, a hidden mass made legible through its effects on another world. Uranus had become more than a newly found planet. It had become evidence. The importance of this episode is sometimes flattened into a simple story of success, as if Uranus drifted. Mathematicians calculated, Neptune appeared, and the matter was cleanly settled. The deeper reality is more instructive. The calculations were difficult. The predicted positions were not perfect in the modern sense. And the orbital history of Uranus is complicated by the fact that gravitational interactions among giant planets are subtle over long timescales. Yet the broader triumph remains extraordinary. The mismatch in Uranus's motion was real enough to point beyond itself. An unseen outer planet did exist, and the method used to find it showed that the solar system could be read dynamically, not merely observed. One body could reveal another through strain, discrepancy, and residual motion. In that sense, Uranus altered the practice of planetary science as much as it altered the map of the solar system. It taught astronomers to treat anomalies not as embarrassment, but as instruction. It also introduced a more unsettling possibility, one that remains with astronomy to this day. Once a hidden planet has been found through gravitational disturbance, the method acquires a certain permanence. Later generations inherit not only the discovery, but the habit of thought that made it possible. This is one reason Uranus still hovers quietly in discussions of proposed distant worlds such as Planet 9. The situations are not identical, and caution is necessary. The evidence for Neptune emerged from repeated discrepancies in the orbit of a known planet, under conditions that could be mathematically framed with increasing confidence. The modern case for a distant, unseen planet in the far outer solar system is built from the clustered orbits of small remote bodies whose dynamics are still actively debated, and alternative explanations remain under discussion. yet the historical echo is unmistakable. Uranus once showed that the map of the solar system was incomplete, and that its incompleteness could be detected indirectly. Ever since then, astronomy has had to live with the possibility that motion may reveal what light has not yet shown. There is another layer to this story as well. Uranus itself was only visible in the sky because it was bright enough, under good conditions, to be seen from Earth, even though it had long escaped recognition as a planet. It had been recorded before Herschel without being understood. That fact gives its history an unusual texture. Uranus was both hidden and visible, present and overlooked. Then, after its formal discovery, it became the means by which something genuinely unseen was found farther still. The planet occupies a threshold position in the history of knowledge. It stands between the ancient visible cosmos and the modern inferred one. Before Uranus, the solar system still carried some of the feel of a finished arrangement. After Uranus, that confidence became harder to defend. Beyond Saturn there was another world. Beyond Uranus there was Neptune. And once such expansions occur, the outer darkness no longer feels empty in the old way. It feels provisional, open to revision. This is part of why Uranus matters even when it is not the main object of attention. It changes the terms of what attention itself can detect. Its orbit once refused to fit the model, and instead of dissolving into error, that refusal widened the known architecture of the Sun's domain. It is one of the rare cases where a planet's importance comes not only from what it is, but from what it forced science to do. To study Uranus was to confront the limit of a system and then move beyond it. To calculate Uranus carefully was to discover that precision can become a form of exploration. A faint blue world at great distance became the hinge on which a larger planetary order turned. By the time Neptune entered view, Uranus no longer appeared simply as the seventh planet. It had become the intermediary between presence and inference, between observation and theory, between the visible solar system and the one that still had to be drawn. Its motion had not merely crossed the sky. It had exposed a hidden structure waiting beyond the edge of accepted knowledge, and in doing so it left behind a harder lesson than discovery alone. Sometimes the most important thing a planet can reveal is not itself, but the disturbance it leaves in the path of everything thought to be understood. At solstice on Uranus, the sun does not rise and set in the ordinary planetary sense. It circles. Over one pole it remains in the sky for years beyond easy human measure, tracing slow motion above a world that turns quickly beneath it, while the opposite pole stays in darkness just as long. This is the first point at which Uranus stops feeling like a distant variation on familiar planets and begins to feel like a place arranged according to a different seasonal geometry. On Earth, the axis is tilted enough to produce winters and summers, but not enough to overturn the basic pattern of daily life. Day and night still alternate everywhere except near the highest latitudes, and even there the departures are limited and local. On Uranus, the tilt is so extreme that the exceptions become the rule. The planet's axis lies almost in the plane of its orbit, which means that over the course of its long year, sunlight falls across the globe in ways that make the usual planetary map of climate much harder to apply. Each pole experiences around 42 years of continuous daylight, followed by around 42 years of continuous night. The equatorial regions, which might be expected to preserve some version of ordinary alternation, do so only part of the time and under conditions that are still deeply unlike those on the inner planets. The whole world has been turned into a test of what happens when a planet's spin and orbit no longer cooperate in the familiar way. That seasonal structure begins with the simple fact that Uranus moves slowly. One orbit of the Sun takes 84 Earth years, so each season lasts about 21 Earth years. This already stretches the meaning of season beyond what human experience is built to understand. A season on Uranus is not a passing atmosphere of weather, or a temporary rearrangement of cloud and light. It is an epoch in the rhythm of the planet, long enough that an entire generation on Earth can begin and end while Uranus remains in essentially the same broad solar orientation. Yet within that immense seasonal timescale, the planet still rotates once in roughly 17 hours. The clouds, where they are visible, sweep around fast. Winds move, the atmosphere turns. There is a rapid day-like rhythm imposed on top of a seasonal pattern that barely shifts at all from one year to the next by human standards. This combination of quick rotation and extreme axial tilt produces a sky that would be disorienting even before the deeper climatic consequences are considered. Near the poles during solstice, the sun would seem to move in circles without setting, its height changing slowly over years rather than dramatically over hours. At other latitudes, the behaviour becomes more complicated, especially closer to the equinoxes, when Uranus presents its equator more directly toward the sun and the geometry begins, briefly, to resemble the more familiar planetary arrangement. Equinox on Uranus is not ordinary, but it is the closest the planet comes to it. During that part of the orbit, day and night alternate more evenly across much of the globe, and the solar illumination becomes distributed in a pattern that planetary meteorology can treat with slightly less strain. These periods are scientifically important because they offer the best chance to compare Uranus with broader atmospheric expectations. They also reveal how quickly the visual character of the planet can change as the illumination angle shifts over years and decades. The poles brighten or dim, cloud structures become more or less apparent, subtle bands emerge more clearly in some wavelengths than others. Uranus does not merely pass through seasons, it slowly reconfigures what parts of itself are exposed to sustained observation. One of the strangest consequences of this geometry is that averaged over the course of a Uranian year, the poles receive more solar energy than the equator. That statement seems almost backward when measured against common intuition. On Earth, the equatorial zone receives the greatest average solar input because the sunlight strikes more directly there through the year, while the poles receive less and remain colder. On Uranus, because one pole spends such a long interval facing the sun so directly during solstice, and because the planet later reverses this arrangement as it continues around the sun, the annual average ends up favouring the poles rather than the equator. It is a rare case where the simple expectation carried over from terrestrial experience breaks down at the level of planetary design. Yet the atmosphere of Uranus does not respond with an equally simple inversion. The equator is not merely colder because it receives less sunlight on average. In fact, temperature patterns and atmospheric behaviour do not line up neatly with the solar geometry at all. This is where the seasons of Uranus stop being a striking curiosity and become a serious scientific problem. If sunlight alone dictated the upper atmosphere, one set of patterns would be expected. If internal heat was strong and well mixed, another might emerge. Uranus instead appears strangely subdued. It emits very little excess internal heat compared with the other giant planets, especially Neptune, which is similar in size but much more energetically active. That missing internal energy matters because on gas giants and ice giants, solar heating is often only part of the story. Deep heat rising from within helps drive circulation, storms, and large-scale atmospheric structure. Uranus seems to have very little of that available, or at least very little that escapes in a way that is easy to measure. The result is a world whose seasons are driven by an extreme solar arrangement, but whose atmospheric response remains unexpectedly muted in some respects, and unexpectedly complex in others. This helps explain why Uranus long seemed bland in visible light. When Voyager 2 passed by in the 1980s, the planet appeared comparatively featureless, especially beside the more dramatic atmospheres of Jupiter, Saturn, and Neptune. But later observations, particularly in infrared, and with more advanced telescopes, began to show that the calm surface impression was incomplete. Bands, hazes, bright features, polar caps, and discrete storms all emerged under better conditions and at more favourable moments in the seasonal cycle. What had looked nearly empty turned out to be subtle rather than simple. Seasonal change appears to play a major role in that subtlety. As Uranus moves away from equinox towards solstice, the polar regions can brighten, and collar-like structures have been observed forming around the poles. The exact cause is still not fully resolved, but methane condensation, haze production, and changes in atmospheric circulation are all likely involved. Here again, the planet refuses to yield a clean answer. There is enough evidence to see the transition, but not enough to reduce it to a single tidy mechanism. This ambiguity is part of what makes the Uranian seasons so compelling. They are not merely long, they are diagnostic. They offer a way of watching a tilted planet respond over decades to a highly unusual distribution of sunlight, while forcing atmospheric science to account for weak internal heat, complex chemistry, and incomplete data all at once. There is also a quieter consequence that extends beyond Uranus itself. Many exoplanets discovered around other stars occupy dynamical states more extreme than those of the classical planets in the solar system. Some likely have strong tilts. Some may be tidally altered, seasonally exaggerated, or locked into orbital arrangements that make Earth seem almost exceptionally well behaved. Uranus, in that sense, is not only a strange local world, it may be one of the nearest natural laboratories for understanding what severe axial tilt does to a planet over long timescales. If the solar system had no Uranus, planetary scientists would still know in theory that such a configuration was possible, but the theory would be poorer for lacking an actual case. Uranus provides one, and not a simplified one. It provides a case complicated by chemistry, cloud physics, heat flow, and observational limitation. Even the sunlight itself arrives differently there, both weak because of distance and uneven because of orientation. The seasons unfold under dim illumination, with the sun nearly 20 times farther away than it is from Earth. Noon on Uranus is never bright in the interplanetary sense. The pale light reaches a world already cold beyond ordinary intuition, where methane helps colour the atmosphere and the energy budget runs close to the margins of detectability. This is why the seasonal system of Uranus feels so difficult to summarise. It is not just that one pole sees decades of day and the other decades of night. It is that the entire climate response to this arrangement remains partly unresolved. The poles receive more annual sunlight, yet the atmosphere does not simply organise itself into an inverted Earth-like pattern. The planet rotates quickly, yet its seasonal transitions crawl across generations. The visible disk can look quiet even while significant atmospheric restructuring is taking place. What appears at first to be an elegant consequence of geometry opens instead into a layered problem of circulation, chemistry, timing, and hidden heat. By the end of it, Uranus no longer looks like a planet with strange seasons. It looks like a planet for which the very idea of season has had to be rewritten, stretched from a familiar cycle of winter and summer into a deep, slow alternation of light and darkness, whose atmospheric meaning is still being worked out under a sun that never quite behaves there the way planetary habit would expect. A planet almost 20 times farther from the sun than Earth might seem easy to understand thermally. It should be cold because little sunlight reaches it, colder still because that light arrives weak and diluted, and quieter than the giant planets closer in because distance reduces the energy available to stir weather. In the broadest sense, Uranus does fit that expectation. Its cloud tops are among the coldest places measured in any planetary atmosphere in the solar system, and the sunlight that falls there is faint enough that noon would resemble a kind of prolonged twilight compared with the inner planets. Yet the thermal story of Uranus does not become simpler as the numbers grow smaller. It becomes stranger. The difficulty is not merely that Uranus is cold. The difficulty is that it seems too cold in the wrong way, and too quiet for reasons that remain unsettled. Planetary atmospheres are not governed by sunlight alone. The giant planets also release energy stored in their interiors, leftover heat from formation and, in some cases, heat generated or redistributed by deep physical processes that continue long after the planets have settled into mature form. Jupiter emits far more energy than it receives from the Sun. Saturn does the same. Neptune, though smaller, still radiates a strong excess of internal heat and drives a dynamic atmosphere marked by powerful winds and vigorous meteorology. Uranus stands apart. It appears to release very little extra heat into space beyond what it absorbs from sunlight. That difference sounds technical at first, but it reaches into nearly every part of how the planet is understood. A giant world should still be cooling from its formation. It should have internal energy to lose. It should, at least in broad outline, resemble Neptune more than it does. Instead, Uranus looks muted, as though a large fraction of its primordial heat has either already escaped, become trapped in a difficult-to-move interior structure, or is somehow not reaching the visible atmosphere in the way models would prefer. This is one of the central puzzles of the planet. The upper atmosphere of Uranus reaches temperatures near the floor of what a major planet can sustain, while still remaining an atmosphere at all, and that extreme cold is not fully explained by distance from the Sun. Neptune is farther from the Sun than Uranus, and yet does not present the same thermal restraint. That comparison is what gives the problem its force. If Uranus existed alone, its dim outer cold might seem almost self-explanatory. But Neptune stands nearby as a counterexample, a similar ice giant exposed to even weaker sunlight yet more internally active and more meteorologically expressive. The pair should have clarified one another. Instead, they sharpen the disagreement. Why should two related planets diverge so strongly in internal heat flow? Why does one seem able to send energy upward while the other appears comparatively sealed? Once that question is asked, Uranus stops looking merely frigid and begins to look thermally obstructed. Several ideas have been proposed, and each helps illuminate the problem without fully closing it. One possibility is that the interior of Uranus is strongly stratified, layered in such a way that heat does not move upward efficiently. In a more convective planet, warm material from below rises, cool material sinks, and internal heat gradually escapes through large-scale circulation. If Uranus contains composition gradients that stabilize the layers against overturning, then heat could become trapped at depth. The interior would still possess energy, but the path from deep mantle to outer atmosphere would be narrowed. This is an appealing explanation because it links the planet's weak emitted heat to structure rather than to absence. The energy may not be gone, it may simply be bottled up. That distinction matters because a planet that lost its heat early and a planet that still has heat but cannot easily transport it are not the same kind of object. They would have different histories, different interiors, and different implications for how ice giants form and evolve. Another possibility reaches back toward Uranus's tilted past. If the planet was struck by a large body early in its history, the consequences would extend beyond axial tilt alone. A giant impact could have rearranged internal layers, altered angular momentum, changed how material mixed, and perhaps even affected the long-term escape of heat. Some simulations suggest that an oblique collision could tip the planet while preserving much of its outer structure, but the details remain model-dependent. The appeal of this line of thought is that it offers a single ancient event with multiple long shadows. The tilt, the moon's arrangement, and the suppressed heat flow might all reflect a common disruption. Yet impact explanations also carry a burden. They must do enough without doing too much. They must produce the modern Uranus without erasing the features that still need to survive. That broader setting matters only because it makes the thermal problem harder, not easier. Even if a collision played a role, the present-day atmosphere still has to be explained in its own right. The atmosphere is composed mostly of hydrogen and helium, with methane contributing the blue-green colour by absorbing red light. High in the atmosphere, methane can condense into clouds under the right conditions, and deeper levels likely host more complex cloud chemistry involving other compounds over long time scales. Seasonal illumination changes interact with this structure, altering hazes, cloud brightness, and circulation. Because Uranus is tipped so severely, sunlight arrives in a profoundly uneven pattern over the course of its year, and this should influence atmospheric motion. Yet the atmosphere does not display a simple solar response. The poles receive more average sunlight over a Uranian year than the equator, but the thermal pattern does not reduce to an inverted Earth-like arrangement in which more sunlight simply means more warmth and stronger visible activity. The observed atmosphere is subtler than that. Part of the challenge lies in the timescales involved. Uranian seasons last decades, and the atmosphere may respond slowly, storing or redistributing energy in ways that are difficult to reconstruct from the short interval of modern observation. Human instruments have watched Uranus carefully for only a small fraction of one Uranian year. That means even a genuine seasonal pattern can be hard to distinguish from temporary variability or from a lagged response that has not yet fully unfolded. A world that changes over decades is difficult to diagnose within a few observing campaigns. This is especially true when much of the atmospheric structure is faint in visible light and reveals itself better in infrared wavelengths, where temperature contrasts and cloud layers stand out more clearly. As telescopes improved, Uranus began to appear less blank. Bands emerged, storm systems became visible, polar brightening and seasonal collars were detected. The planet was not as still as Voyager's first close images had suggested, but the new complexity did not dissolve the thermal mystery, it deepened it. A cold atmosphere can still be active, and a muted heat source does not imply total meteorological calm. Winds on Uranus can be fast, discrete storms can appear, cloud features can shift and evolve. The question is not whether the atmosphere moves, it plainly does. The question is what energy budget sustains and organizes that motion when the planet seems so reluctant to radiate internal heat. In planetary science, energy is not an abstract bookkeeping detail. It is the difference between a world that merely sits under sunlight and a world that churns from within. The smallness of Uranus's excess heat therefore changes how every observed feature must be interpreted. A storm is no longer just weather. It becomes evidence of how little energy may be needed to generate visible disturbance, or evidence that energy can still be locally concentrated even if the globe as a whole appears thermally restrained. A bright polar cap is no longer only a seasonal marker. It becomes a clue about radiative balance, haze formation, atmospheric circulation, and the way sunlight interacts with a planet whose internal contribution seems unexpectedly weak. Even the cold itself has layers of meaning. It signals not just low temperature, but a possible failure of communication between the deep planet and the outer sky. There is also a larger consequence beyond Uranus. Ice giants are thought to be common in planetary systems beyond the Sun. Many exoplanets discovered so far are roughly in the size range between Earth and Neptune, suggesting that worlds with deep, volatile, rich interiors may be among the most typical planets in the galaxy. If Uranus is an ice giant with an unusually blocked or unusual thermal interior, then understanding it becomes more than a matter of local curiosity. It becomes a test case for a whole class of planets that may be widespread elsewhere. A single unresolved energy budget in the outer solar system begins to matter at galactic scale. And still the observational base remains thin. One flyby, intermittent telescopic campaigns, and a long wait between major seasonal milestones are carrying much of the scientific burden. The hidden warmth of Uranus may be absent, trapped, delayed, redistributed, or only poorly measured in the layers where it matters most. Each possibility changes the planet's story. What remains missing is not the awareness that something is wrong with the simple picture. What remains missing is the decisive evidence that would show whether Uranus is a world that lost its heat, a world that buried it, or a world whose deep interior still holds more energy than the outer atmosphere is willing to reveal. The phrase ice giant sounds orderly enough, as though Uranus belongs to a clear category whose meaning can be taken almost at face value. It suggests a larger version of an icy world, perhaps something frozen through and through, wrapped in cold, distant stillness beneath a pale outer sky. But almost nothing about the interior of Uranus rewards that first impression. The name survives because planetary science needs classes, and Uranus does indeed differ from Jupiter and Saturn in broad composition, carrying a larger fraction of so-called ices such as water, ammonia, and methane. Yet the word ice here does not mean slabs, crusts, or calm frozen layers waiting in the dark. It is a historical label for chemicals that condense at low temperature, not a simple description of physical state inside a massive planet. Deep within Uranus, those materials are subjected to pressures and temperatures so extreme that the ordinary categories of solid, liquid, and gas begin to lose their everyday boundaries. This is why Uranus resists simple naming. It is not a gas giant in the way Jupiter is often imagined, but neither is it an icy sphere in any familiar sense. It is a planet whose structure moves beyond the language that first tried to contain it. From the outside, Uranus appears almost insubstantial, a smooth atmospheric globe with no visible surface and no stable landmarks. Yet most of the planet's mass does not reside in the thin outer atmosphere that gives it its colour. The atmosphere itself, though visually dominant, is only a relatively shallow outer layer compared with the deeper body below. It is composed mostly of hydrogen and helium, with methane present in smaller amounts, and that methane absorbs red wavelengths of sunlight, leaving the blue-green appearance that has become the planet's signature. This upper envelope is important because it is what telescopes see first, what cloud systems animate, and what sunlight touches most directly. But it is not where Uranus mainly exists as a planet. The deeper mass lies below, in regions that no camera has seen and no spacecraft has entered, where pressure mounts rapidly and familiar chemistry is forced into unfamiliar forms. Beneath the atmosphere, models point to a vast interior layer enriched in water, ammonia, methane, and other volatile materials surrounding a denser rocky core. The old language would call that middle region an icy mantle, but even that phrase risks misleading calmness. The deeper question is not merely what these materials are made of, but what state they occupy under Uranian conditions. They are not expected to sit as simple frozen deposits. Temperatures in the interior rise to thousands of degrees, while pressure becomes enormous. Under such conditions, water can exist as a dense, hot fluid rather than anything like terrestrial ice. Ammonia and methane likewise enter regimes far removed from common chemical intuition. Some portions may behave as ionic or supercritical fluids, carrying heat and charge while remaining neither ordinary liquid nor ordinary gas. The interior of Uranus is therefore best understood not as a stack of familiar substances, but as a set of deep physical environments, each forcing matter into states that are difficult to imagine without careful theory. That distinction matters because planetary categories can become deceptive when they rely too heavily on surface language. To call Uranus an ice giant is useful only up to the point where it becomes a picture in the mind. If the picture is of a frozen giant, it is wrong. If the picture is of a smaller Jupiter, it is wrong in a different way. Uranus sits between those intuitions and unsettles both. Its average density is higher than that of Saturn and Jupiter, which already hints that a greater fraction of heavier materials must be present inside it. But its outer appearance remains soft, gaseous, and cloud-wrapped. The planet is physically large, about 4 times Earth's diameter, yet much less massive than Jupiter, and only modestly more massive than Neptune. This combination produces a world of broad volume without overwhelming compression in the outer layers, and that helps explain why the gravity at its cloud tops would not feel violently different from Earth's despite the vast difference in total size and composition. The bulk of Uranus is spread through layers that are deep and dense, but not compressed to the same extremes found in the larger gas giants. Its structure is therefore intermediate in more than one sense. It is an outer giant planet, but not one built on exactly the same template as Jupiter and Saturn. It is rich in volatiles, but not dominated by frozen stillness. It is massive, but not so massive that hydrogen and helium define the entire body. Much of the scientific importance of Uranus comes from this in-between character. In planetary formation theory, the distinction between gas giants and ice giants is not a minor bookkeeping choice. It points toward different histories of accretion, different balances of material in the early solar system, and possibly different migration pathways while the giant planets were still assembling. Jupiter and Saturn appear to have captured large envelopes of hydrogen and helium before the primordial gas disk disappeared. Uranus and Neptune seem to have followed a different route, ending with much smaller hydrogen-helium envelopes relative to their total masses and much larger fractions of heavier volatile substances. Why that happened is still part of the broader problem of planetary origin, but the finished result is clear enough to matter. Uranus is not merely a scaled-down gas giant. It belongs to a separate architectural class, and yet even that class becomes unstable when Uranus itself is examined closely, because the similarities between Uranus and Neptune do not erase their differences in heat flow, atmospheric behaviour, and internal expression. The very category that helps place Uranus also begins to fray under its weight. Seen from the inside outward, the planet may begin with a central rocky region made of silicates and metals, though the exact size, composition, and sharpness of its boundaries remain uncertain. Above that lies the great volatile-rich mantle, which likely contains most of the planet's mass. Above that again, the hydrogen-helium atmosphere grades outward into the visible cloud tops. But these are not simple, clean borders like the cutaway layers of a textbook globe. Under planetary pressure, matter does not always sort itself into neat, discrete shells. Composition can change gradually. Temperature can alter phase behavior in ways that blur distinction. Convection may occur in some zones and be suppressed in others. There may be stable gradients that inhibit mixing, helping to trap heat below. This is one reason Uranus remains difficult to model. The interior is not directly observed, and small differences in assumed layering can lead to larger differences in what the planet should do thermally or magnetically. The structure is suggestive, the mass and radius are suggestive, even the measured gravity field is suggestive. What remains elusive is the exact arrangement by which those clues fit together. The atmosphere adds another kind of misdirection. Because Uranus lacks a solid surface, the word surface itself becomes approximate. In ordinary usage, it refers to the visible cloud tops or to a pressure level chosen as a practical boundary. But physically, there is no place where a spacecraft would descend from sky onto ground in the terrestrial sense. The atmosphere thickens downward, pressure rises, and the planet gradually becomes a deeper fluid body. This is true of all the giant planets, yet on Uranus the effect is sharpened by the relative shallowness of the outer gas envelope, compared with the denser, volatile, rich interior below. The visible world is therefore only a skin above a much stranger body. What appears smooth and nearly featureless from a distance is, in structural terms, a narrow entrance into one of the most chemically and physically unusual interiors in the solar system. This interior complexity also helps explain why Uranus has become newly important in the age of exoplanets. Many planets found around other stars fall into a broad size range between Earth and Neptune, and for some of them, there is no close inner solar system analogue. Uranus and Neptune may be the best local examples of a planetary type that is common elsewhere, which makes every unresolved detail about Uranus more consequential than it might once have seemed. To misunderstand Uranus is not only to misunderstand a remote outer planet, it is to risk misunderstanding one of the galaxy's more common planetary forms. The problem is that Uranus does not offer itself as an easy prototype. It withholds. Its atmosphere reveals only part of the story. Its heat flow is subdued. Its magnetic field seems to arise from unusual depths. Its interior chemistry crosses into regimes that cannot be sampled directly. Even the name of its category carries a disguised error if taken too literally. In that sense, Uranus is not just an example of an ice giant. It is a warning about how unstable categories become when they are built from distant appearances rather than deep physical states. By the end of this view inward, the planet no longer resembles the pale, quiet orb first seen in telescopes. It becomes a layered body of rock, hot volatile fluid, compressed chemistry, and relatively thin atmospheric gas, all assembled into a world whose label is useful only so long as it is handled carefully. Uranus is called an ice giant because planetary science requires a term, but the term does not settle the planet. It only marks the beginning of the difficulty, because below the blue-green clouds lies a body that is neither truly gaseous nor truly icy in the ordinary sense, but something denser, hotter, and more physically ambiguous than the old language ever promised. Methane, high in the atmosphere of Uranus, seems harmless enough as chemistry goes. It is a simple molecule, one carbon atom bound to 4 hydrogen atoms, familiar on Earth as a gas associated with marshes, fuel, and trace atmospheric effects. On Uranus, it also helps shape the planet's colour, absorbing red wavelengths from sunlight and leaving behind the blue-green cast that makes the world look calm from afar. But the deeper methane is carried into the planet, the less ordinary it remains. Pressure rises, temperature climbs, the distances between atoms are forced inward. Bonds that are stable near the cloud tops or in terrestrial laboratories begin to enter a regime where chemistry is no longer guided by everyday expectation. It is here, deep below the visible atmosphere, that Uranus gives rise to one of its most enduring and arresting ideas, the possibility that carbon from methane is compressed into diamond and falls through the interior like rain. The image is famous because it is so striking, but its scientific appeal does not come from visual drama alone. It comes from the fact that Uranus provides a plausible environment in which ordinary molecules may be broken apart and rebuilt into something far denser under crushing planetary conditions. This is not a fantasy layered on top of the planet from outside. It begins inside the physics of the world itself. The broad logic is straightforward, even if the details are not. Uranus contains a large, deep mantle enriched in water, ammonia, methane, and related volatile compounds. As depth increases, pressure reaches immense values, and temperatures rise to thousands of degrees. Under such conditions, methane may no longer remain chemically intact. The carbon and hydrogen can separate, and once freed from its original molecular arrangement, the carbon may be forced into more compact structures. Diamond is one such structure, a crystalline form of carbon stable under high pressure. In laboratory experiments, shock compression and other techniques have shown that hydrocarbons can indeed yield diamond-like forms when exposed to sufficiently extreme conditions. That does not prove that the deep interiors of Uranus and Neptune are literally filled with glittering gemstones in the everyday sense. But it does strengthen the central idea that carbon chemistry there may undergo a profound reorganization. The phrase diamond rain survives because it gives a name to that reorganization in motion. If solid carbon forms at depth, it would tend to sink through the surrounding material. In that sense, rain is an acceptable image, yet the reality, if it occurs, would be far stranger than any weather analogy suggests. The relevant environment is not an atmosphere of open sky and cloud in the terrestrial sense. It is a deep planetary mantle where matter behaves as hot, dense fluid under pressures and temperatures that have no easy counterpart at the surface of Earth. Diamond there would not be a jewel. It would be a phase of carbon moving through an alien medium, perhaps as grains or larger fragments before entering still deeper states. What matters scientifically is less the romance of the image than the implication that Uranus may sort its elements by pressure in ways that affect interior layering, heat transport, and long-term evolution. Carbon is not the only substance transformed under such conditions. Water itself may become superionic, with oxygen atoms occupying an ordered lattice while hydrogen ions move through it in a fluid-like way. Ammonia and methane may mix with water in exotic states that no simple textbook diagram can fully capture. The deep mantle of Uranus is therefore not a quiet ocean of recognizable liquids. It is a compressed chemical world where the category of substance remains familiar, while the behavior becomes extreme. Diamond formation, in that context, is one expression of a broader principle. The interior does not preserve matter in the form seen near the surface. It remakes matter according to pressure, temperature, and composition, producing phases that may be stable only inside giant planets. Several versions of the diamond rain hypothesis have been discussed over the years. In the simplest form, methane breaks down at depth, diamond forms, and the resulting carbon falls downward through the mantle. In more elaborate versions, the carbon may continue into layers where temperature and pressure favour different arrangements, perhaps even accumulating in a deep carbon-rich region. Some models have imagined a liquid carbon layer at sufficient depth, with solid diamond fragments sinking into it. These possibilities remain difficult to test directly, but they are not arbitrary inventions. They follow from efforts to map probable phase behaviour onto the known mass, radius, and interior conditions of Uranus and Neptune. The problem is that the relevant regimes are hard both to observe and to reproduce. Laboratory work can imitate pieces of the necessary pressure and temperature space, but only briefly and incompletely. Theoretical calculations can extend further, but they depend on assumptions about composition and mixing that remain uncertain. This leaves the idea in an unusual scientific position. It is neither confirmed fact nor empty speculation. It occupies the middle ground that Uranus so often seems to favour, where the physics is suggestive, the chemistry is plausible, and the decisive evidence remains out of reach. That middle ground matters because the consequences could reach beyond curiosity. If carbon is separating and sinking through the interior, then gravitational energy would be released in the process. Material moving downward inside a planet is not thermally neutral. It can contribute to internal heating or alter how heat is transported. On Saturn, a somewhat analogous idea has long existed for helium rain, where phase separation in the deep interior may help explain excess heat. On Uranus, however, the situation is more complicated. The planet already appears to emit very little excess heat compared with Neptune. If diamond formation occurs, it has not produced a simple outward thermal signature strong enough to erase that broader puzzle. That does not make the hypothesis irrelevant. It only means the connection between interior chemistry and global heat flow is not straightforward. Diamond rain, if real, may be one process among several in a layered interior, where some forms of energy remain trapped rather than easily ventilated to space. Uranus and Neptune are often grouped together, and the possibility of diamond formation has been discussed for both, because the two planets occupy similar compositional territory. Each one helps support the plausibility of the other, yet they are not identical. Neptune radiates more internal heat and shows more vigorous atmospheric behavior, while Uranus appears more thermally suppressed. If both planets can produce deep carbon separation, then similar chemistry may coexist with different large-scale outcomes. Uranus remains the quieter of the pair, and so the image of diamond rain there carries a special tension. It suggests intense hidden activity beneath an atmosphere that often appears subdued. In exoplanet science, this matters as well. Many planets discovered around other stars are likely to occupy pressure and composition regimes where carbon, water, and volatile-rich materials behave in comparably unfamiliar ways. Uranus therefore offers something more than a local curiosity. It serves as a nearby case study in how giant planets might convert common molecules into uncommon deep matter. Planetary interiors are not passive storage regions for ingredients gathered during formation. They are active environments that continue to process those ingredients long after the planet takes shape. In Uranus, one of the clearest examples of that possibility is the fate of methane itself. A molecule that helps tint the outer atmosphere may, at great depth, become the source of descending carbon. This gives the planet an unusual continuity from sky to interior. The same substance that colours the visible disk may participate in the remaking of the hidden mantle below. Yet the idea remains unresolved in the most important way. No probe has descended into Uranus to sample those depths. No instrument has watched carbon crystallise inside the planet. What exists instead is a converging set of hints from physics, experiment, and modelling, all pointing toward a region where methane should not remain methane forever. That is enough to make the hypothesis serious. It is not enough to settle its exact form. By the end of this descent, the phrase diamond rain begins to sound less like a decorative piece of planetary trivia and more like a compressed expression of a harder truth. Uranus is a world where common chemistry is driven past its familiar limits, where methane may be torn apart, where carbon may sink in dense exotic forms, and where the deep interior may be sorting itself in silence beneath clouds that reveal almost none of the process directly. The attraction of the idea is not only that diamonds may fall there, it is that Uranus may be one of the places where matter most clearly shows that under enough pressure, even a simple molecule can be pushed into becoming part of a completely different planetary order. The rings of Uranus are easy to miss, which is part of what makes them so revealing. Saturn announces its rings even to a small telescope, turning the planet into one of the unmistakable sights of the solar system. Uranus does the opposite. Its rings are narrow, dark, and visually reluctant, so subdued that for most of human history the planet seemed to carry no such adornment at all. When they finally emerged into scientific view in the late 20th century, they did not appear as grand luminous bands but as fleeting interruptions of starlight, subtle enough that their existence first had to be inferred from what they blocked, rather than from what they shone back into space. That method of discovery already suited Uranus. Again, the planet made itself known through indirect evidence, through a structure that announced itself not with brilliance but with discrepancy. In 1977, astronomers observing Uranus as it passed in front of a distant star noticed the star dimming briefly before and after the planet itself crossed the line of sight. The pattern repeated on both sides in a way that could not be dismissed as accident. Something narrow and organized was orbiting the planet. Uranus had rings. Their discovery was scientifically important not because rings were unexpected in the absolute sense, but because the specific kind of rings Uranus possessed forced a more careful comparison among the giant planets. Jupiter has rings, but they are faint and dusty. Saturn's rings are extensive, bright, and structurally elaborate. Neptune's rings are dark and in places incomplete, marked by curious arc-like concentrations. Uranus occupies its own position among them, with a system that is narrow, sharply defined in places, and strikingly dark. These are not broad reflective sheets of fresh ice. They're closer to bands of subdued debris, orbiting in a fragile-looking geometry that seems too precise for a system so dim and collision-prone. What first stands out is their darkness. The particles in many of the main Uranian rings reflect very little light, making them among the least reflective large ring structures in the solar system. Wet soil on Earth would in some cases reflect more. That low brightness matters because ring systems are often imagined as delicate, luminous things, easy to see because sunlight catches them cleanly. The rings of Uranus undermine that picture. They absorb more than they reveal, and their darkness implies a surface composition altered by time, radiation, and repeated processing. Water ice may be present, but not in the bright exposed form that dominates parts of Saturn's rings. Instead, the surfaces appear mixed with darker material, likely rich in radiation-processed compounds that have been chemically altered over long exposure to charged particles and sunlight. In the outer solar system, chemistry does not remain visually innocent for long. Ice can become coated, darkened, and chemically modified. Uranus presents a ring system that seems to have lived through exactly that kind of long weathering. Yet the rings are not simply ancient leftovers drifting unchanged since the birth of the planet. Their age, at least in the visible form observed today, may be much younger than Uranus itself. Some estimates suggest that parts of the system could have formed or been reworked within the last several 100 million years, which is recent compared with the age of the solar system. If that is true, then the darkness of the rings does not mean they are primordial in their current arrangement. It means the material has either been repeatedly processed or produced from parent bodies already rich in darkened matter. This points toward a likely origin in disruption, rather than being a stable remnant from the earliest days of planetary formation. The rings may be debris from shattered moons or from repeated collisions among smaller inner satellites. That possibility gives the rings a recent past rather than an ancient stillness. They begin to look less like a permanent planetary ornament and more like the aftermath of breakage preserved in orbit. This interpretation gains strength from the broader Uranian system. The inner region around Uranus is crowded with small moons whose orbits lie close to the rings and to one another. These bodies exert gravitational influences that can perturb neighbouring paths over time, making the system dynamically tense. A collision in such an environment is not difficult to imagine. A moon broken apart by impact, or destabilized into a destructive encounter, could supply a ring with material. Fine particles would spread and grind against one another. Larger fragments might survive as moonlets or be cleared away. Radiation would darken exposed surfaces. What remains after enough time may be exactly the kind of ring system Uranus now shows narrow, dim, and suggestive of repeated reshaping. The rings are also interesting because some of them are narrower than simple dynamics would seem to favour. Ring particles do not naturally arrange themselves into permanently tidy boundaries without some mechanism helping to maintain the structure. Collisions, gravitational interactions, and slow spreading should tend to blur narrow rings over time. At Saturn, small shepherd moons help confine certain rings by using gravity to keep the particles organised. Uranus shows at least some evidence of similar shepherding, but not in a way that explains every narrow feature cleanly. This is where the system begins to feel less settled. A ring that remains thin and sharp invites the question of what is holding it together dynamically. If the answer is a moon, that moon should be found, or at least inferred plausibly. If the answer is more complicated, involving resonances, self-gravity, or collisional behavior, then the ring becomes a test case in orbital mechanics rather than a solved detail. Uranus often works this way. A visible structure becomes less important than the hidden discipline required to preserve it. The rings, therefore, do more than add visual complexity to the planet. They expose a small-scale version of the same theme seen elsewhere in the Uranian system stability that may depend on underlying tension. Voyager. Two transformed understanding of the rings in 1986 when it flew past Uranus and imaged the system directly. Before that encounter, much of what was known came from occultation data and careful ground-based observation. Voyager revealed not only the existence of multiple narrow rings, but also gave a better sense of their arrangement, their darkness, and the broader environment in which they orbit. Even so, the flyby was brief. It provided a glimpse rather than a sustained campaign. Later observations from the Hubble Space Telescope and from large ground-based observatories added further rings and refined the picture, showing that the system extends farther than first assumed and includes faint dusty components beyond the better-known narrow bands. What emerged from these combined observations was not a single simple ring structure, but a family of rings with different widths, brightnesses, and probable histories. Some are dense and sharply bounded, others are more diffuse. Together they form a system that looks less like a single object and more like a continuously negotiated zone between moons, fragments, dust, and gravitational discipline. Their darkness also changes the emotional scale of the rings. Saturn's rings feel architectural, almost serene in their brightness and order. Uranus's rings feel more forensic. They look like evidence. They suggest collision, attrition, and retention at the margin of visibility. Because they are so faint, they seem to belong to the same broader temperament as the planet itself, a world whose most important structures often have to be inferred carefully rather than admired at once. Even their youth, if confirmed, adds to that impression. A relatively recent ring system around such an old planet implies that Uranus is not a finished relic, but a place where significant rearrangement may continue long after formation. The giant planets are often imagined as mature worlds whose major features settled early and then endured. The rings of Uranus imply a more active afterlife, one in which impacts, orbital instabilities, and gravitational confinement can still produce visible consequences on long but not primordial timescales. There is also a useful reversal here. Rings are often treated as secondary to planets, decorative features orbiting around the main body. Around Uranus, the rings instead deepen the central mystery. They speak to the instability of the inner system, to the fate of nearby moons, and to the broader question of how a planet tipped so violently into its present orientation still maintains a complex family of delicate orbiting structures. If Uranus suffered a giant impact in its past, the rings may be very distant descendants of that upheaval, either directly or through the long instability it left behind. If not, then the rings still testify to a history of collision and fragmentation operating under unusual planetary conditions. Either way, they are not incidental. They are part of the evidence that Uranus remains a world shaped by damage that has not entirely finished expressing itself. By the end of this view, the rings no longer appear as faint lines circling a quiet outer planet. They become thin records of disruption, darkened by radiation, narrowed by incomplete explanation, and held in place by a balance that looks temporary even when it lasts. Their faintness does not diminish them, it sharpens them, around Uranus. The dimmest structures may be the ones that say most clearly that the system is not as calm as it first appears. Closest to the rings, where the space around Uranus looks at first like a thin and orderly zone of dark bands and empty distance, a crowded moon system is already at work. Small inner satellites move through a region so tightly packed that calm becomes difficult to trust. These moons are not large enough to dominate the planet's attention in the way Titan does at Saturn or Ganymede does at Jupiter. Yet together they reveal something just as important. Uranus is surrounded by a family of bodies that appears less settled than the word family implies. Their orbits lie close, their mutual perturbations matter, and the boundary between moon and ring material is not always conceptually clean. Some may help confine rings. Some may have supplied ring debris in the past. Some may be temporary survivors in a system that still carries the possibility of future collisions. The moon system of Uranus, taken as a whole, does not feel decorative. It feels like an extension of the planet's instability into orbit. In total, Uranus has 27 known moons, and even that simple count carries something unusual. Unlike the moons of many other planets, which are often named from mythological lineages connected to the Roman or Greek gods, the moons of Uranus draw largely from English literature, especially the works of Shakespeare and Alexander Pope. The naming choice gives the system an oddly different cultural tone, as though even the vocabulary around Uranus has slipped free of the usual planetary pattern. But the deeper difference is physical, not literary. These 27 moons are typically grouped into 3 broad populations: the inner moons, the 5 major moons, and the irregular outer moons. The division is useful because each group appears to tell a different part of the Uranian story. Closest in lie the small inner satellites, intimately entangled with the rings. Farther out orbit the major moons, large enough to have substantial geological histories and, in some cases, differentiated interiors. Beyond them are the irregular moons, distant bodies likely captured rather than formed in place, moving as reminders that Uranus is not only a planet with satellites, but also a gravitational collector of wandering debris. Seen together, these groups form something like a layered archive. The innermost moons record ongoing dynamical crowding. The major moons preserve ancient internal and surface histories. The outer irregulars hint at encounters and acquisitions from beyond the original system. The inner moons are the most immediate expression of instability. Many are small, dark, and difficult to observe in detail, but their modest size does not make them dynamically unimportant. In a crowded orbital region, even small masses can matter over time. Each satellite exerts gravity on the others, slightly nudging orbital paths, changing resonances, and contributing to a web of perturbations that may remain tolerable for long intervals before eventually forcing closer encounters. This is one reason the inner Uranian system is often described as precarious. It is not chaos in the sense of sudden disorder, but a tightly constrained environment in which the future cannot be projected indefinitely with complete confidence. Some of these moons may not preserve their present arrangement over very long timescales. Collisions or orbital rearrangements are plausible in the distant future, and if such events occur, the products may feed ring material or create new small bodies that start the process again. In that sense, the inner moons and rings are part of one evolving system rather than 2 neatly separate categories. One of the best known of the inner moons is Puck, not because it is especially large by planetary standards, but because it was seen relatively clearly during the Voyager 2 flyby and became one of the first recognizable faces of this crowded inner realm. Puck is irregular in shape, dark in appearance, and heavily cratered, like many small bodies that have spent long ages collecting impacts without enough gravity or internal activity to erase them. Yet even Puck, the largest of the inner moons, is still small compared with the major satellites farther out. That difference in scale matters because it marks a transition from fragments that are mostly records of bombardment and orbital dynamics, to worlds that may have had enough internal energy to reshape themselves, at least in part. Beyond the inner group lie the 5 major moons Miranda, Ariel, Umbriel, Titania, and Oberon. They are often presented simply in order of distance, but together they represent the true middle kingdom of Uranus, large enough to hold geological memory and perhaps hidden interior complexity. Titania is the largest, followed by Oberon, while the others occupy smaller but still significant sizes. None approaches the scale of the largest moons of Jupiter or Saturn, yet that does not make them simple. These are not mere enlarged asteroids. They are substantial, icy, rocky bodies whose surfaces record impact histories, tectonic patterns, chasms, bright deposits, and in some cases signs that internal processes once mattered greatly. Their darkness varies, their albedos remain generally modest, and their surfaces are old enough in many places to preserve dense crater populations. But age alone does not define them. Several of the major moons show evidence that they were not frozen into complete inactivity from the beginning. Mixtures of water ice and rocky material, possible differentiation into denser cores and lighter outer layers, and the chance of subsurface liquid zones at some point in their histories all suggest that Uranus's major moons once occupied a more active range of possibilities than their cold present appearance first suggests. Ariel, for example, appears younger and more resurfaced than Umbriel, whose darker face looks older and more inert. Titania and Oberon preserve large impact features and tectonic expressions that hint at expansion, fracturing, or internal evolution. The differences among them matter because they imply that Uranus's moon system did not produce a single repeated outcome. Even within one planetary family, the same broad starting materials may have led to divergent histories depending on size, internal heat, orbital context, and the timing of major impacts. The orientation of these moons adds another layer of strangeness. Because the major satellites orbit in Uranus's equatorial plane, and because that equatorial plane is itself tipped so extremely, the moons share the planet's sideways arrangement. Their orbital lives unfold within the same abnormal seasonal architecture that governs Uranus itself. For long intervals, one hemisphere of a moon may remain exposed to sunlight, while the other endures deep darkness. Depending on the season of the Uranian year, this means the moons are not merely attached to a strange planet. They participate in its strangeness, their cycles of illumination, their polar conditions, and the long-term distribution of sunlight across their surfaces all belong to a tilted system that departs from the common planetary pattern almost from the start. A moon system around an upright planet would already be a complex dynamical environment. Around Uranus, the entire orbital stage has been rotated into something more unusual. Then, beyond the major moons, the system opens outward into the irregular satellites. These are smaller, more distant, and generally interpreted as captured objects rather than bodies formed from the same circumplanetary material as the major moons. Their orbits are wider and often more eccentric or inclined, signalling a different origin story. They do not feel like native members of a settled household. They feel acquired, retained by Uranus after passing close enough under the right circumstances for gravity to convert a wandering body into a permanent, though often distant companion. Captures of this kind are valuable because they preserve evidence of the broader traffic of the outer solar system. A giant planet does not interact only with what formed beside it. It also acts as a net, occasionally holding onto bodies that once moved independently through the colder reaches beyond the sun. Among these irregular moons, Sycrax is one of the largest known, but even the largest remains small compared with the major satellites. Their significance lies less in individual geology than in what their existence implies about Uranus as a gravitational participant in a wider environment. The moon system therefore spans three different kinds of history at once. The inner moons speak of crowding, perturbation, and ring-related disruption. The major moons speak of internal structure, resurfacing, bombardment, and long-lived geological memory. The irregular moons speak of capture and the wider population of small bodies in the outer solar system. Few planetary systems present these layers so clearly in one place, and around Uranus, all of it is shadowed by the larger suspicion that the planet's own violent past may have shaped the moons from the beginning. If Uranus was knocked onto its side by one or more giant impacts early in its history, then the present satellite system may not simply be primordial. Some moons may have reformed from debris after the event. Others may preserve surfaces altered by that ancient rearrangement. The entire family may be, in some sense, the survivors and descendants of a system once broken and reassembled. That interpretation cannot be applied carelessly, but it gives the moons a different role in planetary science. They are not just companions, they are evidence. Each orbit, each composition estimate, each cratered face, and each sign of geological divergence becomes part of the attempt to understand whether Uranus merely acquired a strange tilt or whether the whole system was rebuilt around it. By the end of this survey, the moons of Uranus no longer appear as a simple inventory of names and sizes. They become a layered system of fragments, worlds, and captures, all moving around a planet whose own history may have left them in a state that is stable only by degree. The inner region hints at future collisions, the outer region preserves signs of acquisition, and the major moons hold the most difficult record of all the possibility that beneath their dark and quiet surfaces lies the long aftermath of a planetary system forced into a new shape. Among them, one moon in particular begins to stand apart, because its surface looks less like gradual aging than like a world broken and put back together under conditions that still have not been fully explained. Miranda does not look like a moon that arrived at its present form by patient accumulation alone. Even in the brief images returned by Voyager 2, its surface carried the visual shock of interruption, as if several different worlds had been pressed together without entirely blending into one another. Vast fault canyons cut across older terrain. Cratered plains stand beside regions marked by younger, more complex patterns. Great chevron-like features and banded structures seem almost imposed onto the older surface rather than grown naturally out of it. Among the major moons of Uranus, Miranda is the one that most clearly resists a calm reading. It appears broken in some profound sense, or at least reshaped so deeply that simple gradualism no longer feels sufficient as explanation. That is why Miranda matters far beyond its size. It is not the largest moon of Uranus, it is not the darkest or the most massive, but it may be the clearest satellite-level record of violence in a system already shadowed by the suspicion of catastrophic planetary change. The fascination of Miranda begins with contrast. On one hand, it is small, only a few hundred kilometers across, and small icy moons are often expected to cool quickly and become geologically limited. Their gravity is weak, their internal heat budget is modest, their ability to sustain long-term tectonic or cryovolcanic activity should be constrained compared with larger bodies. On the other hand, Miranda's surface looks too complicated to have remained a simple, inert object throughout its history. It contains some of the tallest known cliffs in the solar system, enormous scarps suggesting extension or collapse on a dramatic scale. It contains regions called coronae, great oval to polygonal zones where the terrain is grooved, ridged, and deformed in ways that imply internal movement or resurfacing. The moon does not merely show impacts layered over time, it shows signs that parts of its crust were reworked, uplifted, fractured, and perhaps partially remade. That is the tension at its centre. A small moon should have had limited means to renew itself. Yet Miranda presents surfaces that look renewed in places all the same. Several explanations have been proposed, and each one reveals a different path by which a moon can preserve the memory of disruption. One possibility is that Miranda was once shattered by a major impact and later reassembled under its own gravity. In this view, the patchwork appearance of the surface reflects literal reconstruction, fragments falling back together into a body whose outer layers never became fully uniform again. The appeal of the idea lies in how directly it addresses the visual evidence. Miranda really does look, at first impression, like an object made from incompatible pieces. But this explanation also carries difficulties. A complete shattering and reassembly would have to preserve enough coherence to produce the modern moon without erasing all internal structure, and the expected outcome may not match every observed terrain boundary as cleanly as the simplest version of the story suggests. The surface seems strange enough to invite the metaphor of a reconstruction, yet the actual mechanics may have been more selective and more complex. Another explanation emphasizes tidal heating. If Miranda once occupied an orbital resonance with one of Uranus's other moons, repeated gravitational flexing could have warmed its interior. That heat might have softened ice, driven internal differentiation, promoted tectonic disruption, or even enabled episodes of cryovolcanic resurfacing. Once the resonance ended, the heat source would diminish, leaving behind a surface that preserves the record of a more active past now long gone. This idea has strong scientific appeal because it does not require total destruction. It links Miranda's complexity to a process known elsewhere in the solar system, where tidal forcing can generate intense geological consequences. Europa, Enceladus, and Io all demonstrate in different ways that orbital dynamics can become internal heat. Miranda, though much smaller, may have briefly shared in that principle during a more dynamically energized chapter of Uranus's satellite history. The problem is not that either explanation fails absolutely. The problem is that the surface may preserve evidence of both impact and internal deformation, layered in a sequence that remains difficult to reconstruct from one flyby's worth of close observation. This is part of what makes Miranda so valuable. It is not merely a curiosity with dramatic cliffs. It is a record of competing processes whose relative importance is still not fully settled. A moon can be struck, flexed, fractured, partially melted, and resurfaced over time. And the final terrain can carry traces of all of those histories at once. On Miranda, the question is not simply what happened. The question is which form of violence mattered most, and when. That uncertainty would already make the moon important on its own. Around Uranus, it becomes even more significant because it sits inside a larger system where violence may not be an isolated theme but a structural one. The planet itself is thought to have suffered a giant impact or sequence of major impacts capable of tipping its axis. The inner moons orbit in a region that appears dynamically unstable on long timescales. The rings may be remnants of shattered satellites. Several major moons show signs of internal differentiation and ancient tectonic modification. In that setting, Miranda stops looking like an exception and begins to look like a concentrated expression of a broader Uranian condition. The system may not have been built once and left alone. It may have been broken, heated, tilted, perturbed, and in places rebuilt. Miranda's surface, with its abrupt terrain boundaries and towering scarps, preserves that possibility in a form too direct to ignore. Its cliffs are especially arresting because they suggest extension on a scale difficult to reconcile with a moon of modest size. The Verona Rupi Scarp, often cited among the highest known cliffs in the solar system, rises over a vertical range that would dwarf terrestrial canyon walls. Features like this are not merely decorative accidents of erosion. They imply tectonic stretching, collapse, or crustal displacement under forces strong enough to reorganize the outer shell of the Moon. On a body as small as Miranda, such forces point back toward either internal heating or external disruption, and perhaps toward both. The surface does not read as the outcome of slow-impact gardening alone. It reads as a crust that has been asked to yield. The coroni reinforce that impression. These large, strangely patterned regions differ from surrounding cratered terrain in both texture and apparent age. Their grooved bands and concentric structures have often been interpreted as sites where warmer material rose from below, deforming the crust and creating zones of renewed surface formation. If that interpretation is correct, then Miranda was not simply broken from above. It was active from within, at least for a time. That possibility matters because it means small icy moons may preserve far richer thermal histories than their size alone would suggest, especially when placed in a dynamically evolving orbital system. Uranus's other major moons broaden the theme, even if none matches Miranda's surface eccentricity so strongly. Ariel appears comparatively youthful in places, with canyons and resurfaced regions suggesting a history of internal activity. Titania and Oberon preserve large fractures and impact basins that hint at tectonic response and deep structural evolution. Even Umbriel, the darkest and seemingly most inert of the major moons, belongs to a family too varied to be explained by a single frozen template. The moons do not all tell the same story, but they do point toward a system where geology, collision, and orbital forcing have all mattered. Miranda simply speaks the loudest in visual terms. There is also a deeper interpretive lesson in its fractured face. Planetary systems are often imagined from the top down, with the main planet treated as the dominant actor and the satellites as passive attendants. Uranus encourages a different view. Its moons are not merely orbiting markers of mass. They are archives of the system's history, storing evidence that the planet itself cannot present directly. Uranus hides much of its past beneath clouds and within its inaccessible interior. The moons expose parts of that past on their surfaces. A moon can keep a scar where a planet keeps only a consequence. Miranda, in this sense, becomes a witness. Whether it was shattered and reassembled, tidally heated into geological activity, or subjected to both in sequence, it preserves the visible grammar of a history that was not gentle. This matters not only for understanding one moon, but for refining the larger picture of Uranus as a planet that may have reached its current form through profound disruption. By the end of Miranda's evidence, the idea of Uranus as merely tilted begins to feel inadequate. Tilt sounds geometric, almost abstract. Miranda restores force to the story. It suggests that the Uranian system may bear the marks of events energetic enough to deform moons, destabilize inner regions, generate ring debris, and leave major satellites with divergent geological paths. A broken world around a broken axis is not proof of one grand unified catastrophe, but it is the kind of evidence that keeps the catastrophic interpretation alive. Miranda does not settle the argument, it changes the scale of it. What looked like an odd planet with peculiar seasons begins to resemble the center of a system still carrying the visible aftermath of ancient violence. Written not only in the posture of the planet itself, but in the fractured face of the moon that orbits closest to looking reassembled from ruin. The magnetic field of a planet is usually imagined as one of its most disciplined features. It rises from deep within, aligns broadly with the spin of the world that generates it, and extends outward in a shape that, while distorted by the solar wind, still reflects a recognizable internal order. Earth follows that pattern closely enough to make it feel intuitive. Jupiter and Saturn, though much larger and governed by different internal materials, also preserve magnetic arrangements that can be described without overturning the usual picture. Uranus does not. Its magnetic field is not centered neatly inside the planet, and it is not closely aligned with the axis around which the planet rotates. Instead, it is tilted steeply, offset from the geometric center, and carried around by a world that is itself already rotating almost on its side. The result is one of the strangest magnetospheres in the solar system, not simply because the field is unusual in shape, but because it seems to begin in the wrong place and point in the wrong direction. This matters because magnetic fields are not decorative planetary traits. They are signatures of hidden interiors. They record where electrically conducting material moves, how deep that motion occurs, and what large-scale structure the inside of a planet is willing to sustain. When Uranus breaks the expected pattern, it does so from within. A planetary magnetic field is generally produced by a dynamo, a process in which conducting fluid moves inside the planet and converts kinetic energy into organized magnetism. On Earth, this happens in the liquid outer core, where molten iron circulates under the influence of rotation and convection. In the gas giants, the conducting region is thought to involve metallic hydrogen at great depth. The essential logic is that a planet needs electrically conducting material, sustained motion, and a geometry capable of reinforcing the field rather than letting it decay away. Once that mechanism operates, the resulting field can extend outward into space, carving out a cavity in the solar wind and producing a magnetosphere. On Uranus, the existence of a magnetic field means the dynamo requirement is being met somewhere inside the planet. But the geometry of the field suggests that the conducting region and the flow patterns that sustain it are not arranged in the familiar way. The field is tilted by roughly 60 degrees relative to the planet's rotation axis, and the magnetic center appears displaced from the planet's physical center by a substantial fraction of the radius. This is not a minor wobble. It is a large structural asymmetry. If Earth's magnetic field were organized in the same way, the ordinary picture of north, south, and center dipolar symmetry would become difficult to recognize. On Uranus, that difficulty is the normal state of affairs. The most likely explanation is that the dynamo of Uranus does not operate in a deep central core analogous to Earth's. Instead, it may be generated in a comparatively shallow shell of electrically conducting fluid within the volatile-rich mantle. This possibility fits with broader ideas about the interior of the ice giants, where water, ammonia, and methane under extreme pressure may enter ionic or superionic states capable of carrying charge. If the conducting region forms a shell rather than a centrally dominant sphere, and if the convective flow within that shell is complex or uneven, then the resulting magnetic field can become strongly non-dipolar and offset. In that sense, the field of Uranus is not merely strange. It may be a clue that the deep conductive engine of the planet occupies a different physical regime from the one operating in Earth, Jupiter or Saturn. What makes this even more compelling is that Neptune shows a broadly similar magnetic oddness, though with its own specific geometry. Together, the two ice giants suggest that this class of planet may favour dynamos generated in outer or intermediate conducting layers rather than in deep central regions alone. If so, the magnetic field of Uranus is not only a peculiarity of one planet, it may be part of a wider rule for a planetary category that remains poorly understood. Yet Uranus still pushes the matter into a more extreme form because its entire planet is already tipped sideways. The rotation axis lies nearly in the orbital plane, and then the magnetic axis departs strongly from that rotation axis in turn. This means the magnetosphere is not just tilted relative to space in some simple, steady manner. It is swept around in a rolling planetary geometry that produces a highly time-variable interaction with the solar wind. As Uranus rotates, the magnetic field orientation presented to the surrounding plasma changes dramatically. A more upright planet with a modest magnetic tilt can maintain a relatively stable, global magnetospheric structure over each rotation. Uranus cannot. Its magnetosphere tumbles through changing configurations as the planet spins, like a field attached to a rotating object already misaligned with the broader architecture of the solar system. The consequences extend far into space. The solar wind, a continuous outflow of charged particles from the Sun, encounters the magnetic field and is deflected around it, stretching the nightside field into a long magnetotail. On Earth, that tail extends away from the Sun in a comparatively familiar configuration on Uranus, because the planet is tipped over and the magnetic axis is itself strongly offset. The tail becomes twisted into a corkscrew-like structure. It does not simply stream backward in a clean line. It coils as the planet rotates, preserving the strange geometry of the field in motion. This is one of those cases where a hidden internal asymmetry produces a visible large-scale structure in space. The shape of the magnetotail becomes a remote expression of the planet's inner and rotational disorder. What begins as a question about deep conducting fluid ends as a helical pattern millions of kilometers long. Voyager 2 provided the only direct close measurements of this system when it flew past Uranus in 1986. Without that encounter, the magnetosphere would still be largely a theoretical expectation, inferred from radio signals and indirect reasoning. Voyager revealed the field's dramatic tilt and displacement, transforming Uranus from a planet assumed to have a magnetic field into a planet whose magnetic arrangement itself demanded explanation. Yet, as with so many Uranian discoveries, the flyby created as many questions as it answered. A single encounter samples a magnetosphere under one set of seasonal and solar wind conditions, not across the full range of its changing states. Uranus was near solstice at the time, which means the observations captured the magnetic system under one especially unusual illumination geometry. Another flyby at a different season might see a significantly different magnetospheric expression. A dedicated orbiter, watching over time, could map changes no single pass can resolve. In the absence of such a mission, scientists have had to build understanding from one extraordinary but limited snapshot. The field also shapes the radiation environment around Uranus. Charged particles trapped in the magnetosphere can strike the rings and moons, altering surface chemistry through irradiation. This helps darken icy materials, generate processed compounds, and modify the optical properties of particles exposed over long timescales. In that sense, the magnetosphere is not isolated from the visible Uranian system. It acts back upon it. The darkness of the rings, the altered surfaces of small moons, and the chemistry of exposed ice may all carry, in part, the signature of magnetospheric processing. The field is therefore both a consequence of interior structure and an agent of surface change. It links the unseen planet to the visible one. There is a further implication as well. If the magnetic field arises in a shallower conducting shell rather than a deep central zone, then the same interior stratification that may help suppress outward heat flow could also be related to how the dynamo operates. The thermal puzzle and the magnetic puzzle may not be separate mysteries after all. They may be different outward expressions of one underlying structural fact. Uranus may be layered in a way that both traps heat and concentrates electrically conducting motion into an unusual region. This remains an inference, but it is the kind of inference Uranus repeatedly encourages. One anomaly begins to connect with another, the tilt, the thermal restraint. The volatile rich mantle and the off-center magnetic field start to look less like isolated oddities and more like a coherent, if still incomplete, planetary type. What makes the magnetosphere especially important is that it removes any temptation to treat Uranus as merely a strangely oriented exterior shell. The planet's oddness is not superficial, it is rooted in the deep body. A world can have unusual seasons because its axis was tipped. It can have unusual rings because its moons collide. But an off-center, highly tilted magnetic field tells a harder story. It says the inside of Uranus is organized differently enough to produce a magnetic geometry that standard planetary intuition does not easily absorb. The field does not end the mystery. It changes the depth of it. By the time the magnetic axis is traced outward into its twisted tail, Uranus no longer appears as a planet that simply fell sideways and stayed that way. It appears as a world whose hidden engine runs under conditions unlike those of the other major planets, sending that difference all the way into surrounding space. The magnetic field begins in a place not yet directly seen, but its consequences are unmistakable. Around Uranus, even the invisible architecture seems displaced, skewed, and resistant to tidy planetary rules. In January of 1986, a single spacecraft crossed the Uranian system and turned a distant blue-green abstraction into a place with rings, moons, magnetic asymmetry, atmospheric detail, and unresolved physical pressure concentrated everywhere at once. Voyager 2 did not arrive at Uranus as an orbiter or a long-term observer. It did not break into orbit, circle through the seasons, or watch the planet over years as changing light moved across the poles. It came once, passed through, gathered what it could, and continued outward. Yet that one encounter remains the foundation of nearly everything direct and close that is known about Uranus. The importance of the flyby lies not only in the images it returned, but in the kind of scientific transition it created. Before Voyager, Uranus was a planet seen mostly as a disk, its details inferred from telescopes and from the logic of planetary comparison. After Voyager, Uranus became a system with texture. Its moons were no longer only points of light, its rings were no longer only occultation signatures. Its magnetic field was no longer assumed to be ordinary. Its atmosphere was no longer simply a distant wash of colour. The flyby did not solve the planet. It made it real enough for the unsolved parts to become sharper. That is why the mission still stands as both revelation and limit. The approach itself already carried the quiet drama that often marks major moments in planetary science. Uranus had been known since the late 18th century, but no spacecraft had ever visited it, and the outer solar system is measured in travel times long enough to absorb human decades. By the time Voyager 2 reached Uranus, the mission had already transformed knowledge of Jupiter and Saturn. It arrived not as an isolated project built for one target, but as part of a chain of exploration in which gravity assists and precise timing allowed one machine to move outward from giant planet to giant planet. Uranus became reachable because earlier worlds had bent the path correctly. That long connected journey gives the flyby an unusual place in exploration history. Uranus was not the opening act of a dedicated campaign. It was the next threshold crossed by a spacecraft already carrying the accumulated momentum of previous discoveries. When the encounter finally came, the geometry of Uranus imposed its own severe terms. The planet was near solstice, meaning one pole was turned strongly sunward and the seasonal illumination was highly uneven. This shaped what Voyager could see. The southern hemisphere was more strongly lit, while the northern hemisphere remained largely hidden in long darkness. As a result, the flyby captured Uranus under one very particular seasonal expression, rather than as a fully balanced globe. That matters because a single close visit to a planet with seasons lasting decades cannot help but be incomplete. Even the best instruments can only observe the hemisphere and atmospheric state presented at that moment. Voyager therefore offered not a total portrait but a slice of a planet, a record of Uranus under one lighting arrangement, one magnetic orientation, one stage in a year far longer than any human mission had yet had time to witness. The images it returned were initially surprising for their restraint. Compared with Jupiter's bands or Saturn's layered cloud structures, Uranus looked smooth, nearly plain, with only subtle atmospheric contrast visible in ordinary light. It was easy at first to treat this as confirmation of a quiet planet, muted and meteorologically simple. But the apparent blandness itself became part of the puzzle. The atmosphere was not necessarily inactive. It was difficult to see. Later improvements in telescopic observation, especially at infrared wavelengths, would reveal more bands, storms, bright features, and seasonal changes than Voyager could show under its conditions and instruments. Even so, the flyby established an important baseline. It showed that Uranus presents itself differently from the other giant planets, and that visible calm does not necessarily imply physical simplicity. The mission also transformed understanding of the rings. Earlier occultation work had already revealed that rings existed, but Voyager showed them directly and placed them into a wider environmental context. They appeared narrow, dark, and more sharply defined than simple expectation might have suggested. The spacecraft added to the inventory of known rings and gave the first close sense of their subdued physical presence. Around Saturn, rings dominate the eye. Around Uranus, they required patience and careful geometry. Voyager confirmed that the system was not decorative in the usual sense. It was delicate, dim, and structurally suggestive, a set of bands orbiting a planet that seemed already predisposed to indirect evidence and hidden discipline. The moons may have been the most immediate beneficiaries of the encounter. Voyager discovered new satellites and returned the first close images of several major moons, revealing a family of worlds far more varied than a distant census of brightnesses could have implied. Miranda in particular emerged as one of the strangest objects in the solar system, with its fractured terrain, towering scarps, and patchwork appearance that still resists a single settled explanation. Ariel, Umbriel, Titania, and Oberon also became more than names and orbital paths. They acquired surfaces, geological contrasts, craters, faults, and histories. Uranus ceased to be just a planet and became a system of worlds, each carrying its own version of the larger mystery. But perhaps the most conceptually disruptive discovery involved something invisible. Voyager measured Uranus's magnetic field and found it to be profoundly misaligned and offset, unlike the centered and broadly ordered planetary magnetospheres that intuition had been prepared to expect. This single result changed the scientific status of Uranus immediately. No longer could the planet be treated as an outer giant that merely happened to be tipped over. Its interior now seemed different enough to produce a magnetic geometry that demanded new thinking about dynamos inside ice giants. And because the flyby also occurred under an unusual seasonal orientation, the magnetosphere was seen in a state no simple analogy to Earth or Jupiter could comfortably explain. The field's tilt, displacement, and rotating interaction with the solar wind opened a new dimension of Uranian strangeness that telescopes alone could not have delivered. Yet the encounter also left behind a scientific problem that has only grown more obvious with time. One flyby is enough to expose surprises. It is not enough to resolve them. Voyager could reveal the existence of complex moons, but not track their histories in detail over time. It could map the magnetic field at one moment, but not watch how the magnetosphere evolves across the long Uranian seasons. It could image the atmosphere under one lighting geometry, but not remain long enough to see how that atmosphere responds as the planet moves from equinox towards solstice and beyond. It could sample the ring environment briefly, but not follow the long-term dynamics of dust, confinement, and possible instability in the inner moon system. In effect, Voyager turned Uranus from a remote unknown into a known unknown, and the distinction is important. After the flyby, the mysteries were no longer vague. They were itemized. They had shape, scale, and location. Scientists could point to specific unresolved questions about heat flow, interior layering, magnetic generation, seasonal meteorology, ring maintenance, and moon geology. But the means to answer those questions directly did not follow. This is what gives Uranus such a particular scientific atmosphere in the decades after Voyager. It is not neglected because it lacks importance. It is neglected because it was revealed to be important by a mission that never had the capacity to stay. Since then, telescopes on Earth and in orbit have continued the work from far away. They have tracked seasonal changes, observed storms, refined ring and moon discoveries, and improved understanding of atmospheric structure in wavelengths beyond visible light. These efforts have been scientifically rich, and they have corrected the early impression of Uranus as almost featureless. But distance imposes limits that no increase in telescope sophistication can erase completely. Telescopes cannot descend into the magnetosphere. They cannot map gravity and magnetic harmonics from multiple close passes. They cannot watch the moons at low altitude or sample the charged particle environment in situ over years. They cannot replace a dedicated orbiter moving repeatedly through the system under changing conditions. This long interval between revelation and return has therefore created one of the most unusual situations in planetary science. A major planet, known for centuries and visited once, remains in many practical ways only lightly explored. The silence after Voyager is not literal, because observations have continued and theory has deepened. It is a silence of proximity. No spacecraft has gone back. The only direct close encounter remains the one that occurred in the mid-1980s, when the planet was seen under one season by an instrument suite designed for a fly-through rather than a residency. Every decade that passes without a return increases the contrast between how scientifically important Uranus appears and how little direct contact has followed the recognition of that importance. This gap matters even more now because the broader role of Uranus has changed. In the age of exoplanets, ice giants are no longer peripheral planetary types. They may represent one of the most common categories of planet in the galaxy. To leave Uranus so sparsely explored is therefore not only to postpone understanding of one strange outer world, it is to postpone understanding of a class of planets that may be widespread around other stars. Voyager provided the indispensable first close look, the encounter that made all later questions possible. But first looks do not become complete understanding simply by aging. They remain first looks. The Uranus revealed in 1986 still waits, in many respects, for its second conversation. By the end of Voyager's passage, the planet was no longer an almost featureless blue disk in the dark. It had become a system of dark rings, damaged moons, displaced magnetism, subtle weather, and withheld internal logic. What remains remarkable is not that one flyby changed so much. It is that after changing so much, it was left for so long to stand alone, a single brief crossing still bearing the weight of nearly everything direct that humanity knows about one of the solar system's most rule-breaking worlds. By the time all of Uranus's separate oddities are placed beside one another, the temptation is to treat them as a collection rather than a system. There is the sideways axis, the long polar day and night, the weak outward heat, the volatile rich interior, the possible diamond chemistry, the dark narrow rings, the fractured moons, the off-center magnetic field, and the long scientific silence after Voyager. Each item is unusual enough to hold attention alone, but Uranus becomes most important when those features stop being listed and begin to be read together. Then the planet changes from an assortment of curiosities into something more difficult and more valuable, a world that repeatedly exposes the limits of simplified planetary rules. It does not break physics. It breaks the convenient expectations built around planets that are easier to observe, easier to classify, or easier to compare. Uranus resists the idea that a planet can be understood once it has been named, grouped, and given a few broad physical properties. Instead, it keeps asking a harder question. What if the rule is only the average, and the average fails exactly where planetary history matters most? In many ways, planetary science begins with pattern recognition. The planets orbit the Sun in roughly the same plane. The giant planets possess thick atmospheres and many moons. Worlds farther from the Sun are colder. Rotation produces day and night. Internal heat helps drive atmospheric motion. Magnetic fields arise from conducting fluid in motion deep within a planet. These are good rules, useful rules, and in broad outline they remain true. But Uranus keeps entering those statements and forcing additional clauses into them. Planets orbit in roughly the same plane. Unless one has been tipped so far that its seasons no longer resemble the ordinary planetary case. Giant planets have atmospheres driven by sunlight and internal heat. Unless one seems to withhold much of its internal energy, while still preserving atmospheric complexity. Magnetic fields reflect internal conducting motion. Unless the conducting region is arranged in such a way that the field begins off-center and sweeps through space in a geometry that feels almost improvised. A planetary class can be named from shared composition, unless one member of that class diverges enough from its nearest sibling to expose how incomplete the category remains. This is why Uranus is not just strange, it is instructive. It does not overthrow planetary science. It deepens it by showing where general rules become insufficiently precise. The axial tilt is the clearest example because it is both obvious and system-wide. A planet with a moderate tilt can still be treated within the familiar framework of poles, equator, and seasons. Uranus cannot. Its sideways posture changes illumination, climate logic, the seasonal experience of its moons, the interaction of its magnetosphere with the solar wind, and perhaps even how its past is reconstructed. Yet even here the most important lesson is not the tilt itself, it is the inadequacy of simple explanation. A giant impact can be invoked, and perhaps rightly so. But even that story branches immediately into further questions. Was it one impact or several? How were the moons affected? Did the collision alter the interior strongly enough to suppress heat transport? Could the same event that tipped the planet also have contributed to its magnetic oddness or its satellite architecture? Uranus never allows a single dramatic fact to remain isolated. The moment a cause is proposed, the rest of the planet begins to ask whether that cause can carry enough of the burden. The thermal puzzle pushes the same difficulty inward. A cold, distant planet is expected, a planet that appears to release very little excess internal heat compared with Neptune is more problematic. The contrast with Neptune matters because it turns Uranus from a mere data point into a disagreement. Two ice giants should, in broad terms, illuminate one another. Instead, Uranus complicates the pair. If heat is trapped beneath stable internal layers, then the planet's compositional architecture may be far more important than simple bulk properties imply. If a past impact helped create that structure, then planetary violence becomes part of long-term thermal evolution. If neither explanation is sufficient on its own, then Uranus may be pointing toward a form of internal organization that current models still only approximate. The deeper question is not merely why Uranus is cold, it is why a giant planet can preserve so much outward evidence of complexity while seeming so reluctant to release the energy that should help animate it. The interior continues that resistance to easy framing. Ice giant is a useful term. But Uranus exposes how unstable useful terms become when pressed too literally. The planet is not a giant block of ice, nor is it simply a smaller Jupiter wrapped in hydrogen and helium. It is a layered body of rocky material, hot, dense, volatile, rich fluid, compressed chemistry, and a relatively shallow outer atmosphere, all arranged under conditions that force matter into unfamiliar states. Diamond formation may occur, water may become supersonic, the dynamo may operate in a shell rather than a core. None of these possibilities is merely decorative. They imply that planetary interiors are not passive repositories of ingredients, but active environments where common molecules can be remade into phases that would never exist at the surface of Earth. Uranus therefore breaks another quiet rule: the assumption that the visible planet is a reasonable guide to the real one. On Uranus, the visible disk is only a narrow atmospheric entrance into a much stranger hidden body. The moons and rings carry the argument outward again. A ring system can be treated as a secondary feature until its darkness. Youth and narrow confinement begin to suggest repeated collision, ongoing instability, and incomplete dynamical explanation. A moon system can be treated as an inventory until Miranda appears with a surface that looks as though it remembers destruction more vividly than gradual time. Around Uranus, the smaller bodies do not merely ornament the planet, they preserve evidence that the system has not always been calm and may not remain calm indefinitely. The inner moons perturb one another in crowded space. The rings may be debris from shattered satellites. The major moons record different geological paths rather than one repeated template. The irregular moons imply capture from beyond the original satellite system, taken together. These features make Uranus feel less like a settled planetary household and more like a structure still carrying the consequences of earlier disturbance. This matters because it weakens another simplification, the idea that mature planets are best understood as finished objects. Uranus looks mature in age and location, but parts of its system still read like aftermath. The magnetic field sharpens that sense of rule-breaking perhaps more than any other single feature after the tilt. Planets are expected to have magnetic fields that reflect some deep internal order. Uranus has one that reflects deep internal complication. It is tilted, displaced, and dynamically expressive on large scales. The resulting magnetosphere twists into space rather than simply extending into it. This is not the sort of anomaly that can be set aside as superficial weather. It points directly into the unseen conductive regions of the planet and suggests that the dynamo itself is operating under conditions unlike those of the better-studied giants. When the field is considered alongside the suppressed heat flow and volatile rich mantle, Uranus begins to look as though several mysteries may be connected. The same layered interior that limits convection could also constrain where electrical conduction and organized motion occur. The same history that altered the planet's axial geometry may have helped shape how its deep fluids now behave. A rule broken in one place begins to imply a broader internal logic. Yet the final reason Uranus still breaks the rules is not located in the planet alone. It lies partly in the state of the science brought to it. Uranus remains underexplored. One flyby is carrying too much of the direct burden. Telescopes have added enormously to what is known, but they cannot replace long-duration in situ measurement of gravity. Magnetism, atmospheric structure, charged particles, and moon geology across changing seasons. This means that Uranus occupies a rare position in modern science. It is clearly important, clearly anomalous, and still only lightly sampled at close range. Its unresolved status is not a sign of triviality, it is the opposite. The planet remains unsettled because it has already shown enough complexity to outgrow the evidence currently available. In the age of exoplanets, this becomes even harder to ignore. Worlds in the rough size range of Uranus and Neptune appear to be common in the galaxy. if the nearest local examples of that planetary type remain only partly understood, then a large portion of planetary diversity is being interpreted through an incomplete foundation. Uranus is no longer just a strange edge case at the margin of the solar system. It is a nearby representative of a broader class of worlds that may be among the most common planets in existence. To understand Uranus better is therefore not only to solve a local puzzle, it is to refine the rulebook for planets far beyond the Sun. By the end, the phrase "broke the rules of planetary science" begins to sound less like exaggeration and more like a precise description of what Uranus keeps doing to every tidy model brought near it. It rolls where planets are expected to spin upright. It stores or conceals heat where comparable worlds release it. It hides exotic chemistry beneath a nearly featureless exterior. It surrounds itself with dark rings and moons that preserve the signs of instability. It generates a magnetic field whose geometry seems shifted away from the most familiar planetary design. And above all, it remains just known enough to expose these contradictions without yet yielding the decisive evidence that would make them feel fully resolved. Everything observed so far can be arranged into a plausible story, but not yet into a settled one. And that difference is what keeps Uranus so scientifically important. It is not only a strange planet, it is a reminder that planetary science is still young enough for one quiet blue world, moving slowly in the outer dark, to force the rules to become better than they were before. The longer Uranus is considered, the less it resembles a distant outlier, and the more it begins to feel like a quiet correction written into the solar system itself. Not a correction against physics, but against simplification. A planet can be cold without being simple. It can appear calm while concealing deep structural difficulty. It can carry the marks of ancient violence so thoroughly that those marks become the ordinary condition of its seasons, its moons, its rings, and the invisible field that extends far beyond it. Uranus remains compelling for that reason. It does not overwhelm through brightness or speed or spectacle. It holds attention through a more patient form of resistance, by refusing to become fully settled in the mind, even now, after centuries of observation and one precious close encounter. It remains a world described partly by what is known, and partly by the shape of what still does not fit cleanly together. That incompleteness is not a weakness in the subject. It is part of the subject itself. Some planets are understood by bringing their parts into order. Uranus is understood, at least for now, by recognizing that its order may be stranger than the first rules allowed. Its sideways year, its dim rings, its damaged moons, its hidden chemistry, and its displaced magnetism all belong to the same larger impression, a planet that keeps the evidence of deeper processes just below the threshold of easy resolution. In that way, it remains one of the quietest and most persistent mysteries among the major worlds, not because it hides everything, but because it reveals enough to make the hidden parts matter more. And in the cold outer distance, beneath a pale sun and above an interior still beyond direct reach, Uranus continues its slow passage, carrying with it a version of planetary history that is less tidy, more fractured, and perhaps more representative